we'll get started, right. So, the last aspect that we saw was polarization. Today we are going to just see how to start incorporating the effect of conduction current density, specifically conductivity and the presence of free charges in the medium. The assumption thus far has been that we have medium free from the charges, all right, and now we are going to incorporate that part. The analogous part in transmission line is introducing resistance and conductance in the equivalent circuit for the transmission line section. However, the details are slightly different because here we have both conduction and displacement current densities. So, the interpretations and the number of cases are slightly different, but the analogy is exactly the same as what we saw in transmission lines. Okay. So, in order to start with this, okay, I am going to rewrite the two curl equations for now. Okay. I am going to start with del cross E, and in the prior sessions we have written them in time domain. Okay. Now, along with the introduction of losses, I want to introduce the effect of frequency, because we know already that in the case of transmission line we dealt with j omega L and j omega C. Unless you introduce the frequency, you will not be able to extract the correct value of inductive reactance and capacitive reactance. Similarly, here we want to have the effect of frequency. Specifically, we want to analyze what a material medium will do in general. At high frequencies, how do they behave? At low frequencies, how do they behave? So, we have to introduce the frequency. Okay. So, del cross E is then written as minus j omega mu naught mu r h. The assumption here is electric field and the magnetic field are time harmonic, all right, they are periodic, and the expression will be E naught e to the j omega t and h naught e to the j omega t. Okay. So, when you take a derivative of h naught e to the j omega t, you get j omega h naught e to the j omega t. So, we have just marked h naught here. Again, this part is exactly same as what we did with transmission lines. There we would have had a voltage which was a sinusoid. Specifically, we took a cosine and then we will take a real part of e to the j omega t. So, the same thing is being done here, right. So, again del cross h. Previously, we had neglected conduction current density. Now, we are starting to incorporate the conduction current density also, right. So, this would mean you have a conduction current density J, right. This is coming because of the charge density rho in the medium, right, plus j omega epsilon naught epsilon r E. Okay. So, this was del D del T, all right, and assuming that your medium is isotropic, all right, isotropic, then you will have epsilon naught epsilon r coming into the picture, and then you are also assuming that its frequency independent for the epsilon r value. Okay. The frequency dependence that we are interested in is using the omega, and assuming that even if epsilon r and epsilon naught are going to be fixed, they are going to be fixed, right, and if sigma is going to be fixed, thus omega play a big role in determining whether a material will behave like a conductor or a dielectric. This is the broad question, and we are going to look only at the two curl equations, right. So, we can begin this analysis by saying that if the medium has a conductivity right, and we represent conductivity with sigma, okay, we can write down Ohm's law for the conduction current density. You can say that the conduction current density, which is in amperes per meter, right, is going to be sigma times E. Right. So, this is just Ohm's law. Unit of electric field is volt per meter, all right. So, correspondingly on the left hand side I have included a conduction current density. So, this means that the first equation does not change, all right, because we did not have any conduction current density related term over there, but the second equation del cross H, we can expand J in terms of sigma and E, all right. So, we can substitute sigma E instead of J in del cross H equation. So, we can start with del cross H, okay. You can write this down as sigma E plus j omega epsilon naught epsilon r. Okay. So, you can take the constants out, you can say that sigma plus j omega epsilon naught epsilon r times E. Okay. Can go one step further and we can try to rearrange the terms inside the bracket, all right, and try to see if we can divide this into some real part, imaginary part, etc. All right. Already we have a sigma term which is not dependent on the frequencies, what it looks like, and then we have a j omega epsilon naught epsilon r term. Suppose we rearrange, all right, and we do some distribution of terms, then can we make a different physical interpretation, right. So, what we can do is we can rewrite this as j omega, okay, epsilon naught and then you can rewrite this as epsilon r minus j sigma by omega epsilon naught is the same thing, all right, where we have taken some common terms out and we have rewritten the same expression. The idea is very simple. If you look at the original del cross H equation, we had j omega epsilon naught epsilon r e and you added a j. Suppose I rewrite this down as j omega epsilon naught some new quantity times E, it will resemble the original equation that we wrote for vacuum also, right. It will resemble, but the interpretation is going to be different. So, what we are trying to say here is the term in the bracket, right, we can create a new constant or we can create a new variable name, right, and call this as epsilon r c. C means complex, all right. So, previously we had j omega epsilon naught epsilon r e. Now, we have created a new term, it has a real part and an imaginary part, and we call this as epsilon suffix r c, meaning that we are saying that let us assume that the permittivity, relative permittivity, if it is to be a complex number, then we can account for the conduction current density also, right. Then what happens is the way you write the equation becomes similar to the way you were writing prior to inclusion of j, right. So, you can write this as j omega epsilon naught epsilon r c. It is just a simpler way to write the curl equation. It resembles the original equation that we wrote, except that we have suffixed a c for the subscript of epsilon r, right. So, now this term needs more attention, right. So, this term needs more attention. Previously it was only j omega epsilon naught epsilon r, all right. Now, it is epsilon r c, that means we have created some new term and we have to look into it in detail, that is right. So, we use this constant or variable, right. This case it is known as relative permittivity of conductive medium. You can just say that relative permittivity of a conductive medium. Previously we just had relative permittivity, all right. Now, we are adding something to specify that it could be a conductive medium, it does have conduction current density present, okay. Once again, the epsilon r c is also known as say complex permittivity in some texts or complex dielectric constant, all right. Complex permittivity is easier, complex dielectric constant is kind of weird because you are talking about constant related to dielectric, but you are saying it is complex and you are including some conductivity. It may be confusing for a few people. So, you can just call it as complex permittivity. It includes both displacement and conduction quantities. Okay. So, epsilon r c, the first thing that we note is, let us write down this expression. It has a real part, it has an imaginary part. Okay. One of the things that we notice here is even if you assume epsilon suffix r to be fixed, okay, all right, even if you assume epsilon suffix r to be fixed, that is the real part is fixed, even if you start with some number say 1, and if you start with non-zero sigma and keep it fixed, you can say it is also equal to 1, all right. Epsilon naught is a constant, so 8.854 times 10 to the negative 12, right. But depending on the frequency, epsilon RC can change, right. The first thing that we notice here is even if you keep the relative permittivity, conduction and your relative, absolute permittivity of the vacuum to be fixed, depending upon the frequency or complex permittivity can change, all right. The only way you can remove any frequency dependence in such kind of media is by plugging sigma equal to 0, correct. So, in a pure dielectric medium, it is possible to do that, right, over a wide range of frequencies, but in a conducting medium, epsilon RC depends on frequency. So, this is the first thing that we have to deduce. No matter what you do, it is going to be complex and it is going to be say frequency dependent. Okay. One also can say that the term j that we have used equal to sigma e, all right, is a characteristic of a conductor okay. It is a characteristic of an electric conductor, and epsilon naught epsilon r e is a characteristic of a dielectric. Okay. So, there is some term corresponding to characteristics of a conductor, there is some term corresponding to the characteristics of a dielectric in the most generic case where you write down the complex permittivity. Okay. Now, then the question is the material, I am sorry, usually I turn it off. Okay. So, then the question becomes, could we take the ratio of one quantity to another to determine whether the material is behaving more like a conductor or a dielectric, right. So, we can say that conduction current density divided by displacement current density suppose it is much greater than 1. Okay. Suppose the conduction current density divided by the displacement current density is much greater than 1, or equivalently sigma divided by omega epsilon naught epsilon r is much greater than 1, we call such materials as good conductors. Okay. So, if sigma is divided by omega epsilon naught epsilon r is much greater than 1, we call it as a good conductor, all right. Now, there is a small detail that we have to notice over here, it is not a very big thing, but there is a small detail. Sigma greater than 1 does not automatically qualify for being a good conductor in these cases. You have to take sigma divided by omega epsilon naught epsilon r, and that has to be much greater than 1. Okay. So, the ratio is more important, all right. For example, one can always say that if you keep on increasing the frequency of operation, Okay. Your denominator will keep on increasing. Invariably, you will start with say a fixed value of sigma, and the ratio will be going towards 1 and then less than 1, etc. So, it depends on the frequency, and looking at this expression here, we can say that there is a good chance that at very low frequencies a material will be a very good conductor, but at higher frequencies the same material may actually behave like a dielectric. Okay. So, we can also write down if sigma divided by omega epsilon naught epsilon r is say very much less than 1, you will call this as a good dielectric. Okay. So, the ratio is very much greater than 1, it is a conductor, the ratio is very much less than 1, you can call it a dielectric. So, it means that if you start with fixed values of sigma, fixed value of epsilon r, and as you change the frequency, it is inevitable that at low frequencies you will observe that the material seems to be having large amount of conduction current, alright, compared to the displacement current density, but at very high frequencies the material will be more or less dielectric. This is the way it is, alright. Now, we notice that the ratio goes between very much greater than 1 to very much less than 1, which means that as you increase the frequency, the material has to pass through a frequency where both these quantities are nearly equal, because you cannot go from one to the other without passing through that equality. Okay. So, then you can have a case where sigma divided by omega epsilon naught epsilon r say in the order of 1, right. Okay. So, there will exist a frequency for a material where you cannot figure out whether it is a dielectric or whether it is a conductor. Okay. So, these materials you can just say as it is neither good dielectric nor good conductor. Okay. So, this means that if sigma is approximately equal to omega epsilon naught epsilon r, you can expect that material to be neither a good dielectric nor a good conductor. In other words, you cannot say absolutely if the material is a dielectric or a conductor. This is true for any material, alright. And this happens at specific frequencies for specific materials. For example, if you take copper, it may have a value of sigma, alright, assuming that sigma does not change with frequency at all, and assuming that epsilon r of copper is 1 for all frequencies. You can calculate at what frequency omega sigma will become equal to omega epsilon naught epsilon r. There will exist a frequency where both these components are equal, and after that copper will start behaving more like a dielectric. Okay. So, the trend here is at low frequencies many materials could be very good conductors. At high frequencies the same materials could exhibit dielectric like behaviors. Okay. Now, this is an important aspect because we use metals for interconnects on boards. Okay. Suppose you start increasing the frequency of operation of these chips, and suppose you start increasing the frequency of operation of your entire system, alright. You need to be aware that the best conductors will not behave like the best conductors anymore. Okay. So, it is a very important aspect while designing high frequency circuits or high frequency communication systems, etc. Right. Just to give you an example, all right. All right. For copper, I just looked up a value on the internet. Some standard value people use as epsilon r is approximately equal to 1, all right. Hard to believe, but copper seems to be having relative permittivity of just 1, similar to that of air, all right. But where it differs from vacuum is the very high value of conductivity Okay. So, I have written the distributed parameter 5.6 times 10 to the power 7 Siemens per meter. Okay. It is a very high value compared to epsilon r, right. So, we can say sigma divided by omega epsilon naught epsilon r is equal to 1, omega will be equal to sigma divided by epsilon naught epsilon r, all right. So, we can say that the omega at which this transition happens, right, you can divide it by 2 pi and you will get the frequency in hertz, right. So, that frequency is known as transition frequency. Okay. It is known as transition frequency. In this case, just taking these values, all right, it appears that the frequency in this case where I have taken these particular values is 10 to the power 18 hertz, okay, seems abnormally high. That is simply because I have taken some values which I have assumed do not change with frequency also, okay. But in the simplest case, it does look like at very high frequencies, copper should start exhibiting equal dielectric and conductive behavior, and it is very high, all right. For seawater, all right, I saw that the relative permittivity from some source is about 80, all right, and sigma is 10 to the power minus 3 Siemens per meter. Again, these are not validated sources of this information, but these are some sources that I have picked up just to demonstrate that there is a transition frequency, okay. And in this case, if you do the substitution for sigma divided by omega epsilon naught epsilon r equal to 1 and try to find out the transition frequency from there, it appears that the transition frequency is approximately 225 kilohertz. So, I just wanted to show the high range of frequency and relatively very low range of frequency by appropriate choices of epsilon r and sigma, that is all right. This transition frequency in semiconductors, they also call it as dielectric relaxation frequency. At this place, you will not be able to figure out whether the material is behaving like a conductor or a dielectric. In conventional optics, it is also common to call this as plasma frequency, because you cannot figure out the property as to whether it is a dielectric or a conductor, okay. So, these are just different terms. We will use the term transition frequency. Okay. Now, we can go back and have a look at our modifications to the wave equation. Del square E, all right, can be written as minus omega square mu naught mu r epsilon naught epsilon r E. This is how we would have written it in the frequency domain. We had written it in the time domain before, the frequency domain, assuming that you are having a single frequency source of electric and magnetic fields. This is how you would have written. The only change now we need to make is change epsilon r to epsilon rc to indicate that yes, you are including some conduction current also. In the same way, for magnetic field, del square H, right, is minus omega square mu naught mu r epsilon naught epsilon r h. In this case, to indicate that you are taking care of the conduction current density, just suffix. So, that rearrangement for the permittivity and conductivity is useful, because we can revisit all our equations and add some subscripts, all right, and then we will be good to go, right. Now, let us take this first equation and start looking at the right hand side. Okay. So, once again, you can go ahead and substitute for what is happening to epsilon r c. Okay. You can always substitute for epsilon r c. So, there can be a rearrangement possible on the right hand side. So, I will just rearrange the right hand side, right, j omega mu naught mu r times sigma plus j omega epsilon naught epsilon r okay. is just to say that you can always separate terms, you can always rearrange it, right. You can take some common terms out, but this I believe is hard to remember for the students. It is easier to just remember this, right. So, if you remember this and later on if you want to substitute for epsilon RC, you could always do this and rearrange, it is not a problem. Okay. Now, we can also look at the equation again and say that for majority of materials, okay, for majority of the materials, it is safe to assume that the materials do not have any relative permeability greater than air. Many of the materials are non-magnetic, alright. So, majority of the materials, it is safe to assume that mu r is equal to 1. Of course, when you are doing serious research, you can plug in the exact values and proceed, but it is not incorrect to assume that for a lot of the materials that you will encounter, mu r is actually equal to 1. That just removes one more term from the right hand side of the wave equation, right. So, which means that I can now start to look at the solutions to the wave equation. We already know that there will be a forward and a backward wave, etc. We already know that there will be a propagation constant. Previously, we had only phase constant. Now, because you have included the conductivity part, there will be a propagation constant, and we already know from transmission lines that the propagation constant will have a real and an imaginary part. Real part will correspond to attenuation, imaginary part will correspond to the phase constant. Okay. So, we are going to do the exact same thing as we did in the case of transmission lines. Okay. So, in this case, there are some details that we will add, because in the past we have come across these details. We have to be specific to say that for a plane wave, okay, traveling in the z direction. So, now we are becoming more specific in the way we talk about the plane wave. We are saying that it is traveling in the z direction, and we also know from the prior class that we have to talk about polarization, alright. So, we say that x polarized. So, in the beginning or in the prior classes, we have seen that majority of the time we took Ex and then we took Hy, and then the propagation direction was Z. So, we are specifying that using a verbal statement saying that it is traveling in the Z direction and it is X polarized. Okay. So, the wave equation can then be written as dou square Ex by dou Z square. The left hand side of the wave equation, alright, dou square Ex by dou Z square is equal to minus omega square mu naught. I am assuming mu r to be equal to 1. Okay. So, I will just write down as epsilon naught epsilon RC Ex. Okay. Or like we have seen in transmission lines, we can write this down to be some gamma square Ex. Okay. So, which means what we have done is we have created a new variable. Gamma is going to be square root of minus omega square mu naught epsilon RC. So, we can write this down to be j omega square root mu naught epsilon naught square root epsilon RC. Okay. Again, I have taken the positive square root j. Okay. So, j omega square root mu naught epsilon naught square root epsilon RC. This will be your propagation constant in the case of plane wave in a medium having conduction current. Okay. And now, okay, we also know that by casual look we will make a deduction that we have j omega something, which means that it is purely imaginary, but that is not true. That is the illusion that this substitution for epsilon RC is giving us. One should always remember in the back of the mind that this is again a complex number. So, even though you have written j omega something, here is a complex number. So, you will end up having a real and an imaginary part. Okay. So, you will end up having a real and imaginary part, and the task to separate them is not very simple. Okay. So, I will write down, right. Anyway, I will substitute for the epsilon RC j omega square root mu naught epsilon naught. Okay. And for epsilon RC, we know that the expression is epsilon R minus j sigma divided by omega epsilon naught. Okay. If we put like this, then it becomes clearer that there is a real and there is an imaginary part. Okay. So, one has to be very careful, and it is obvious that there is a real and an imaginary part, but separating them is not very easy. Okay. So, what I did is I just plugged it in Wolfram Alpha on the internet, and I checked what is the real and the imaginary part. Okay. I am not going to go inside how to separate the real and the imaginary parts over here, but I can make use of a symbolic math tool like X Maxima or Wolfram Alpha and quickly see what is the real and the imaginary part. Okay. And I saw that alpha, which is the real part of the propagation constant, in this case turns out to be omega square root mu naught epsilon naught times there is no way I would have guessed this. So, it was justified that I did use a tool to calculate. Okay. Beta is imaginary part of gamma. I am writing down these expressions just for the sake of completeness. I do not believe that you have to remember these for your exams and quizzes. If we come to a stage where you need to make formula sheets, etc., you definitely could do that, all right. But even better will be for me to ask questions that do not involve this kind of expansions. So, we will see to it that that happens. Okay. So, alpha is the real part of gamma, it is the attenuation constant, beta is the imaginary part of gamma, which is the phase constant, all right, and they are very complicated expressions for us to make any direct evaluation, all right. The only thing that one can say is alpha and beta depend on frequency, all right. And I can say that there is omega multiplied by something, and then I have square root of 1 plus sigma square divided by omega square coming over there in the denominator, etc. Generally, I can notice that since there is an omega term coming over here, I can make a general remark saying that as omega increases, alpha could increase, as omega increases, beta could increase. These are the only things that broadly you can make out from here, but the prior argument was much easier to follow than this one. Okay. So, there is only one more term that people often use, okay, which is known as loss tangent. Okay. They use the term loss tangent. Okay. So, this is usually given by sigma divided by omega epsilon naught epsilon r. Okay. So, if you were to consider this in the form of sigma being represented in one axis, j omega omega epsilon naught epsilon r being in another axis, you could mark an angle between the real axis alright, and between whatever value of sigma divided by omega epsilon naught epsilon r is with respect to the origin, right, and it will resemble a triangle and you are taking the tan of that angle, right. So, people call this as loss tangent, alright. So, they also mark it with a term tan delta, okay, and you have sigma divided by omega epsilon naught epsilon r, okay, and higher the value for this, higher is going to be your attenuation, that is all, okay, that we already know, because if sigma is going to be higher, right, because sigma is present in the numerator of alpha, obviously you are going to be having more attenuation, right, which means that the electromagnetic waves that we are talking about, okay. So, tan delta is equal to sigma divided by omega epsilon naught epsilon r is the loss tangent, and usually higher this value, okay, one can immediately notice that you are having this term coming into the picture over here. So, obviously higher is going to be your attenuation, alright. This is another way of looking at it, and there is also some other things that can be used to simplify things, right. Let us take a material for example, where sigma is much greater than omega epsilon naught epsilon r. The reason why I am writing all these things is because in real world you can make some approximations by saying that one is much larger than the other and scratch out terms, so that it becomes easier to simplify. That is why we are doing this in a number of ways. So, if sigma is very much greater than epsilon naught epsilon r, alright, you can write down the propagation constant, alright, to be simply square root of j omega mu naught sigma. You can write down the propagation constant to look like square root of j omega mu naught sigma. Okay. Once again, this will have a real and an imaginary part, okay, and square root of j is usually confusing for some students, right. So, if you want to write down square root of j, the best way to do this is to make use of Euler's theorem, alright. Write it as, e to the j pi by 2, take a square root of that, right, and then you write this down as this is just e to the j pi by 4, right, and you can say that this will be some cos pi by 4 plus j sin pi by 4, that is the only thing, right. One of the advantages of doing this is this gives you a neat 1 plus okay, it is 1 by root 2 times j times 1 by root 2. Okay. The advantage is, if you look at the remaining terms, omega is going to be a real value, mu naught is a real value, sigma is a real value, alright. The only thing that is messing with this real and imaginary parts of this entire expression is this j within the square root. Suppose you write it down in this form, you get a clear real part and a clear imaginary part. So, that becomes easy. So, if you remove square root of j outside, okay, you can write this down as gamma is equal to square root of omega mu naught sigma times 1 plus j the whole thing divided by root 2. So, then it becomes easy to separate what is alpha and beta. Okay. So, in this case one can notice that it is very easy to separate alpha and beta. You will have a j term, alright, and you will have a non j term, that is all. The other observation that we make over here is when sigma is very much greater than omega epsilon naught epsilon r, it is rather a peculiar case where alpha is equal to beta and it is just square root of omega mu naught sigma divided by 2. Alpha is equal to beta and it is equal to square root of omega mu naught sigma divided by 2. This is also something which is simpler. So, if you make some simplifications, in this case we said first mu r is equal to 1. Then we said that if sigma is much greater than omega epsilon naught epsilon r, then you can start cutting terms, and then the expression for alpha and beta becomes much simpler, and then you can make some reasonable deductions. You can take one parameter at a time, increase and see the effect on alpha. Now it is clear that if I increase the value of omega, alpha will increase. If I increase the value of omega, beta will increase. Okay. So, at higher frequencies you will experience higher attenuation in conductive media. Okay. At higher frequencies the phase constant is also higher, that means the wave will go from 0 to 2 pi much faster than what it did in vacuum. Okay. So, these things become clearer if you start making some assumptions, scratch out terms and then looking at a simpler expression. Okay. So, in general one can write down that for non-magnetic media where conduction current density is much higher than displacement current density, or the material is almost a good conductor. Okay. Omega, if it is high, it will have high attenuation and it will have high phase constant. The other way to write this down is if the conductivity is very high, which is the case with these structures, I mean with these materials, right. Sigma is very high compared to epsilon naught, epsilon r in this case. You can also write down that your alpha will be high, beta will be high. These are probably easier to remember than the large expression that you had for alpha and beta. Okay. Okay. So, I hope that now you have some general idea about behavior of materials itself. It is safe to assume that any material at low frequencies will be a good conductor and the same material at very high frequencies will be close to a good dielectric. Okay. So, this is the natural trend. At low frequencies whatever conducts at very high frequencies it will become dielectric. Right. So, there is not much you can do about it. Secondly, at low frequencies alpha is low, that means you can get long range of propagation of electromagnetic wave. Right. So, if you send a plane wave at very low frequency, it will travel a much longer distance in a medium than a plane wave at very high frequencies. Right. So, as you start increasing the frequency of the electromagnetic wave, you will notice that in the same medium it will start propagating lesser and lesser and lesser distance. Okay. So, it means that these things pose some technological challenges. Okay. The evolution of communication has been from low frequency and it is going towards higher and higher frequency of operations. Okay. So, when they had radio waves, right, when they had long range, when they had medium range, when they had short wave communication, all these things, all right, you would have had some propagation distance. They were able to communicate over long distances, but they needed maybe large areas, etc. But then later on we have switched to much higher frequencies. But the challenge is as the frequency increases, the range of your system for communication will naturally decrease because of attenuation present. So, even in the air you will have some content of say water, water vapor, etc. These will also have some tiny amounts of salts and other things, and which will increase the conductivity, and then as high frequencies happen you will end up with alpha becoming higher. Okay. So, this is a practical scenario where one can assume that at low frequencies you can expect high propagation lengths, okay, and you can expect the material to be highly conductive, losses are going to be very low. At high frequencies the materials will heat up very fast, okay, your losses are going to be high, propagation lengths are going to be really low, and this is inevitable. Okay. Now, there is one more thing that we need to look at in the case of plane waves, which is the power. In the case of electric circuits, you would have learnt that if you applied a voltage and the system draws a current of I, then you will multiply the voltage with the current and then you will say that the power is supplied is in watts, the power delivered is in so many watts, etc. In this case, simply because we are dealing with vector quantities, okay, we do not deal with a scalar voltage and a current, we are dealing with vector quantities. Right, the calculation of power is slightly different from that of transmission lines. Okay. So, the power density, okay, okay, is defined as E cross H. Okay. Remember that the power density is a vector, all right. It is a vector, it does have direction, it tells you where is the source, where is the sink. Okay. So, it is a vector. okay, and it is given as a cross product between your electric and magnetic fields. So, the unit for the electric field again is volt per meter, magnetic field is ampere per meter. So, you will have volt ampere per square meter, alright. If you assume that there is no phase difference between your electric and magnetic fields, alright, instead of writing down volt ampere you could use watts and say that it is watts per meter square. Okay. So, dimensionally it is fine, and it means that if your electromagnetic wave is arriving at a particular medium, you will have to take the size of the beam that is hitting the medium, calculate the power density and integrate it over the entire area, because you are having only watts per square meter. To get watts, you will have to integrate this power density over the area in which your beam is hitting, then only you will be able to get the net power, alright, that is crossing a surface. Okay. So, the net outward power, alright, which is P, sometimes it can become confusing. So, I will just use W. It is going to be your surface integral can be E cross H okay. Alright, it is slightly different from how you will calculate in electric circuits or even in transmission lines, because you did not have vector quantities. Okay. So, it is E cross H, which also resembles what we had seen earlier classes for the discussion of the polarization. We had used the right hand rule, where we would use the electric field to be along the index finger, magnetic field along the middle finger, and then you had a direction of propagation to be your thumb. E cross H just represents the thumb, alright. So, the power is going from this side to the other side, which is along the direction of propagation, alright. So, it is safe to assume that the source is somewhere here and the sink is somewhere on this side. Okay. So, you can use the same rule, alright, to figure out where the power is actually going, and there are some more details that we will have to slowly uncover. For example, we have to start looking at how the power depends on space, how the power depends on time, okay, because we are having time harmonic electric field, time harmonic magnetic field. It is quite possible that there is a phase difference between electric and magnetic field. There is no phase difference between electric magnetic fields, alright, and instantaneous power versus average power. Just like in electric circuits, you would have had instantaneous power and average power, you would have had real power, reactive power and apparent power, all those things. So, similarly we will have to see what we can figure out from here, right. So, that will be the goal for the future lecture, right. So, I will stop here.